In this video, I will be explaining load flow analysis using Newton-Raphson method. The Newton-Raphson method load flow analysis is an iterative method which approximates the set of nonlinear equations to a set of linear simultaneous equations using Taylor series expansion, and the terms in the expansion are limited to the first order approximation. Second and higher order derivatives we are neglecting in the Taylor series expansion. So the calculation becomes very simple. If you consider the second and higher order terms, the calculation becomes more complex. So the accuracy of the calculations may increase if we include the second and higher order terms. So in this video, I will be explaining the mathematical background for NR method. Mathematical background for NR method. This is one of the simple derivation they keep on asking in the university exams. So here we are considering the mathematical algebraic equations and we are explaining how the Newton-Raphson method can be implemented in the mathematical analysis. So here we will consider the variables like the x1, x2 like this, x3 etc. up to xn. These are the unknown variables. Similarly, we will consider the y1, y2 etc. up to yn. These are a set of specified quantities. In power system, what happens in any particular bus? So we know some of the known and unknown quantities. Example, if you consider the load bus, the known quantities are P and Q, that is real power and reactive power, and at the same load bus the unknown variables are voltage, magnitude and angle. In the same way, here also we are considered the variables x1, x2, xn are the unknown variables, and y1, y2 etc. up to yn are the specified variables. So now we will be expressing the specified quantities as a nonlinear function of unknown variables. That means, so here the specified quantities y1 is expressed as a function of the unknown variables like this etc. up to xn. Similarly, we can write y2 is f2 of x1, x2 etc. up to xn, and similarly yn is equal to fn x1, x2 etc. up to xn. These set of equations, let us call it as equation number 1. So here we have expressed the specified quantities as a nonlinear function of unknown variables x1, x2, xn up to xn. So now here the unknown variables are assumed initial solution. So that means, let us assume the x1 naught, x2 naught etc. up to xn naught are the approximate initial solution for the equation 1. That is, here I consider the equation 1. No? For this, the initial solution for that is x1 naught, x2 naught. So these are the initial solution for the unknown variables x1, x2, xn. But these are the assumed solution, but they are not the final solution. In iterative method, we will assume the initial values for the unknown variables. So the corrections required for this initial solution is delta x1 naught, delta x2 naught etc. up to delta xn naught. So these are the corrections required for x1 naught, x2 naught and etc. up to xn naught. So now the nonlinear equations can be expressed like this. So here these nonlinear equations are expressed as the modified variables. Example, see here, x1 naught is the initial solution for x1. Correction required for this is delta x1 naught. So this is the unknown variable. Similarly, we have that x2, initial solution is x2 naught, and the correction required for this is, similarly we can consider that up to xn naught plus delta xn naught. So this is the corrections required for the initial solution. Let us include this in the nonlinear equation. We will get similarly like this equation 1 is there, no? We are modifying this equation 1. So that is y1 is equal to f1 instead of x1 naught. So let us consider this correction, comma, x2 naught plus delta x2 naught. Similarly, it will go up to delta xn naught. So this is what so similarly we can write the y2 expression, that is f2. In the same lines you can write x1 naught. So x2 naught plus delta x2 naught. Similarly we can go up to delta. So this will go up to yn. Yn is equal to fn x1 naught plus delta x1 naught, x2 naught plus delta x2 naught, etc. up to xn naught plus delta xn naught. So these set of equations, let us call this equation number 2. So here we have included the correction factors for the unknown variables. If you see the previous page, see equation 1, it deficits the specified quantities as a function of nonlinear function of unknown variables. But these unknown variables in the iterative procedure, we assume the initial solution for x1, x2, x3 like x1 naught, x2 naught, xn naught. So like here I showed, and then the corrections required for these unknown variables are delta x1 naught, delta x2 naught, etc. up to delta xn naught. So when you consider the unknown variable x1, if you include the corrections as well as the initial solution, this is the answer. So let us include these terms in the equation 1. The equation 1 modifies to equation 2, that is y1 is equal to f1 of x1 naught plus delta x1 naught and so on and so forth. So now what we will consider to do is, we will use the technique of linearization of these nonlinear equations by using the Taylor series expansion. Here we are linearizing these nonlinear equations using Taylor series expansion, and here we will consider only the first order terms. The second and higher order derivatives we are neglecting because it becomes more complicated. So equation 2, let us modify by applying the Taylor series expansion. So using the Taylor series expansion, we will modify the equation 2. So that is, this equation 2 is there, no? So we will modify this. So that means, so y1 is equal to f1 of x1 naught, comma x2 naught, etc. xn naught plus delta x1 naught dou f1 by dou x1 plus delta x2 naught dou f1 by dou x2. Similarly it goes. Similarly we can expand till etc. plus delta xn naught dou f1 by dou x1. So y2 equation also in the same lines you can write. So f2 x1 naught, x2 naught, etc. up to xn naught plus delta x1 naught dou f2 by dou x1 plus delta x2 naught dou f2. Instead of f1 you will write x2, f2, that's all, plus remaining terms almost in the same lines you can write f2 dou x1. So this will write up to the specified variable y1, y2, etc. up to yn. So this is fn. So x1 naught, x2 naught, similarly xn naught plus delta x1 naught dou fn by dou x1 plus delta x2 naught dou fn by dou x2 plus etc. Plus last term is delta xn naught dou fn by dou xn. This is n, this is n. So these set of equations, let us call this equation number 3. So what we did, when you see this equation 1, here we have defined the specified quantities in terms of a nonlinear function of unknown variables. Next we consider the initial solution and also the correction factor for the unknown variables x. So equation 2 you got. By Taylor series expansion we consider only the first order derivatives, like here first order derivatives we have considered. We are not considered the second and higher order terms. So by applying the Taylor series expansion we got the modified equation of 2, that is equation 3. So now what we do here is, let us consider the first term in the RHS. See here, first term in the RHS, let us take it to the left hand side and rewrite this equation 3. So we will get this equation, that is y1 minus f1 x1 naught x2 naught etc. up to xn naught is equal to, remaining it remains same, RHS whatever it is there it remains same, that is delta x1 of next to dou f(x1), same lines you can write x2 naught dou f1 dou f1 divided by dou xn. So similarly you can write the second term, second equation, that is this y2 minus x1 naught, same lines, in the same lines you can write, is equal to delta x1, instead of f1 you write f2, remaining it remains same, f2 dou x2 plus etc. Plus dou xn dou f2 by dou xn. Similarly we can write till yn minus fn x1 naught x2 naught etc. xn naught, this is x, is equal to delta x1 naught dou fn divided by dou x1 plus x2 naught dou fn to fn divided by dou x f2, this is fn, this is dou fn dou x2 plus etc. plus you will get last term, that is delta xn naught dou fn by dou xn. So these equation set you can call it as equation number 4. So if you see the equation 3, I consider the RHS first term to the left hand side. So this is how we got the equation 4. So in this equation 4, the LHS terms here, LHS terms, you can write these LHS terms as delta y1, this is delta y1, delta y2, this term you replace by delta yn. So we can rewrite this equation by assuming, that is y1 minus f1 x1 naught x2 naught etc. up to xn naught is equal to delta y1. So similarly you can write this f2 x1 naught x2 naught etc. xn naught equal to delta y2. Similarly you can write this as yn minus fn x1 naught x2 naught xn naught is equal to delta yn. So this is nothing but the LHS terms in the equation 4. So this equation 4 we can modify as equation 5. So that means we can write it as LHS delta y1 is equal to delta x1 naught dou f1 by dou x1 plus delta x2 naught dou f1 by dou x2 etc. etc. Last term is delta xn naught is equal to dou f1 by dou xn. So similarly you can write delta y2 is equal to delta x1 naught dou f1 by dou x1 plus dou f1 by dou x2 plus etc. plus delta x1 naught dou f1 by dou xn. Here second term, second f2 you will get. So similarly we can write till the end, that is delta yn is equal to delta x1 naught dou fn divided by dou x1 plus delta x2 naught dou fn by dou x2 plus etc. plus dou fn by dou xn. So this set of equations, let us call it as equation number 5. So this equation number 5 we can write in the matrix form. That means in the LHS we have delta y1, delta y2 etc. etc. up to delta yn, that is LHS. Then we have RHS 2 matrix. So the last column matrix is delta x1 naught, delta x2 naught etc. etc. delta xn naught. So here if you see the previous equation, see LHS we have delta y1, delta y2 up to delta yn. So here we have considered that, and if you see this RHS, if you write in matrix form you will get the 2 matrix. The last matrix is delta y1, delta, see if you see this delta x1 naught, delta x2 naught, delta xn naught, that is there in the second term in the RHS, and in the first term in the RHS are the first order derivatives of the functions, that is dou f1 by dou x1, dou f1 by dou x2 etc. etc. up to dou f1 by dou xn etc. So here you will get dou f2 by dou x1, dou f2 by dou x2 etc. dou f2 by dou xn. The last term similarly we can write dou fn by dou x1, dou fn by dou x2 etc. dou fn by dou xn. So this is in the matrix form. In the matrix rotation, this you can call it as equation number 6. You can call it in the matrix notation, that is B is equal to J into C. Here B is called residual column matrix. B is called residual column matrix. If you see these elements of the B matrix in the previous equation, this is delta y1, delta y2, delta y1, delta y2, delta yn. This delta y1 is nothing but the difference between the specified quantities and the calculated quantities at the initial assumed solution with the elements of this j and B matrix, if you know, you can find the C matrix elements. So this J is called Jacobian matrix. J is called Jacobian matrix, or it is also called as first derivative matrix, FIR, first derivative matrix. So this first derivative matrix you can easily find. Suppose if you know, example, if you take y is equal to f of x, suppose y is equal to f of x means x square plus 2. So if you assume the initial value of this x as 1, so you can get y of 1 as, so that is 1 plus 2, that is 3. See, you can get the next values. Suppose if you consider dou y by dou x, you will get that is 2x plus 0, 2x plus 0, that is 2x. If you assume the initial value, so the first derivative value, that is dou y by dou x is equal to 2 into 1, that is 2. So that means by having the initial solution, you can find the derivative values with this example I showed. So here in the same lines you can find the residual column matrix. It is the difference between the specified quantities and the calculated quantities in the initial solution, and the Jacobian matrix elements also you can find as shown in this example. And by knowing the B and J matrix, you can find the C matrix. So that means C matrix is nothing but delta x1 naught, delta x2 naught, similarly delta xn naught. So that means we are finding the corrections required for the initial solution. So the initial solution, example, if you take a unknown variable x1, the initial solution we are assumed x1 naught, and it requires the correction for this x1 is delta x1 naught. See, initial solution is assumed and corrections we found, and by adding these two, the x1 variable first iterated value of x1 you can find. Similarly, x2 of 1 you can find. X2 of 1 is equal to initial solution we know and corrections we know. So by adding these two you can find. Similarly, xn of 1 is equal to xn of 0 plus delta xn of 0. So we can find the corrections required, and from that first iterative values you can find. So the new solution, the process is repeated to find the next new solution. That means initially we have assumed x1, x2, xn naught, and we found the x1 naught, we found the x1 of 1, x2 of 1, xn of 1, that is first iterative value. These first iterative values are substituted in the calculation to get the second iterated values of x1, x2, xn, that is second iterated values. So this process continues till the B are in this matrix, B the largest element. So the largest element in the B matrix or the C matrix should be less than the pre-specified value. So if these conditions satisfies, then we will stop the iteration process, and at the end whatever the solution we have, as it satisfies the condition, the finalized values are the unknown variables we found. This is how we can find the unknown variables in the iterative procedure using NR method. So I thank you one and all for your patience listening of my lecture video. Thank you very much.